Building in the tropics is a direct confrontation, specifically an average temperature of 32 degrees Celsius, compounded by a relentless humidity of 83%. For the human body, survival depends on a constant internal core temperature of 37 degrees. When the environment pushes back, the body has to shed that heat immediately. Under normal conditions, we shed heat through conduction, radiation, and convection. But in this climate, those pathways are effectively blocked. When the air temperature is continually near our own skin temperature, heat loss becomes negligible. This biological reality drives us indoors, where mechanical cooling systems now account for 60% of a building's total energy consumption. Most modern skyscrapers are physically incompatible with this environment. They act as massive heat-trapping greenhouses, serving as an energy liability rather than a shelter. In the Global South, green architecture is a mandatory, engineered survival strategy for climate neutrality. It requires treating the entire structure and its surrounding site as a single, calibrated ecological filter. To solve the tropical heat problem, we have to move beyond standard blueprints. We have to design the building strictly from the outside in. The process begins with the site data. Architects must integrate the building's footprint into the local ecology before the first foundation is poured. Trees function as active thermodynamic disruptors. They modify the urban microclimate by intercepting radiation and breaking up convection currents. By utilizing a canopy for radiation blocking and evaporative cooling, designers can actively lower the thermal load of the site before it ever reaches the building's walls. Moving into the building's geometry, the goal is to optimize physical orientation, minimizing the surface area exposed to direct solar gain. This brings us to the most critical metric in tropical design, OTTV, or Overall Thermal Transfer Value. This measures exactly how much heat is transferring through the building's enclosure. High-performance designs aim for an OTTV below 45 watts per square meter. Achieving this requires high albedo roofs to reflect light and low conductivity insulation to choke off heat transfer. Low emissivity windows then harvest natural light while repelling infrared heat. A perfectly engineered passive shell is the ultimate dividing line, determining whether a building is a climate-neutral asset or a massive energy drain. Once the passive shell minimizes the load, active renewable systems are introduced to power the remaining internal services. There is a technical distinction here. Photovoltaic panels convert solar radiation into electricity, while solar thermal systems use that same radiation to heat working fluids. Integrating these active generation systems with a defensive shell allows the tropical building to reach energy neutrality. Inside, the result of this aggressive exterior engineering is a serene, controlled environment. This is the realm of Indoor Environmental Quality, or IEQ, the objective test of a green building's success for the people inside. By stripping away solar heat, occupants gain superior air quality, acoustic comfort, and natural light without the physical stress of the external climate. Because architects can now measure the correlation between these environmental variables and human performance, they can verify the results. Data shows that high IEQ leads directly to improved occupant health and higher work performance. Sustainable architecture is defined by a rigorous adherence to the laws of physics and local ecology. Surviving the extremes of the Global South requires harmonizing every layer, from the shade of the macro tree canopy to the micro coatings on the window glass. Designing meticulously from the outside in produces a highly efficient, living ecosystem that operates in sync with its environment.